Okay, fine. Is the screen visible?
Yes, sir.
Okay.
Yes, sir.
Yes, nice. We'll start. Okay. We'll start with the last class topic. We'll write the state table for JK flip-flop, D and T flip-flops. Then we'll be designing a 3-bit up counter, then down counter, then any other sequence counter also we will design. Okay, right. We start with the we should be clear with the state table. Last class also we discussed a quick refresher. State table for JK flip-flop. So we have in a state table, we have the outputs, we have to determine what should be the inputs. Okay. This is the state table for JK. This is the state table for T flip-flop. Are you taking notes while following?
Yes, sir.
Yes, that will be good because everything is there in your syllabus and these sort of things will be asked in any competitive exams also. Okay, like GATE or any other exam. So it's always good to have notes. Though I give the PDF, try to write in your own handwriting. That's a good thing.
Yes, sir. We are right.
Yes, that's nice. This is the state table for T flip-flop. Okay. So this is the state table for JK, T and D flip-flops. Okay, we have seen this explanation in the last class, how we got this state table, right? Now we'll go into the design of the sequential circuit or synchronous sequential circuit. Okay, why it is called synchronous? Because all the flip-flops will have the same clock or will be triggered at the same clock pulse. That is why they are called synchronous sequential circuit. Synchronous sequential circuit is to design a synchronous sequential circuit is systematic procedure. Okay, first we will design a 3-bit up counter. 3-bit up counter. We know counter is nothing but it will be counting. Up counter means it will be starting from the lowest value, then keep on increasing. How many bits I'm going to use is 3 bits. Okay, so let me say the 3 bits are I'm going to use 3 flip-flops is required. Okay, I have to decide which flip-flop. First thing I'm going to use is a JK flip-flop. Using JK flip-flop. Okay, right. So I have 3 flip-flops. Let me say flip-flop A, B, and C, or else I can say 0, 1, 2. It's up to us. Okay, let me say 0, 1, 2. That's the easy to remember. Or else A, B, C also okay. Right. So let the 3 flip-flops be A, B, C flip-flop. So first flip-flop output is QA. QA. Second flip-flop output is QB. Third flip-flop output is QC. Okay, so what is the lowest value using 3 bits? Using 3 bits is 0, 0, 0. Up counter, this is the first value, initial value. Then it will be keep on incrementing. See, if my audio is not okay, please intimate me. Okay.
It's okay, sir.
Okay, okay. Okay. First is all are 0. Here at this side I will write the decimal for our reference. First count is 0, then 1, then we have 2, 3, 4, 5, 6, 7. Okay. In binary, 1 is 001, 2 is 010, 3 is 011, 4 is 100, 5 is 0101, 6 is 110, 7 is 111. Okay, so these are this is the binary sequence I should get at the output. Okay, right. So what I'm doing here is can use okay, this is the binary sequence I have to follow. Now, first thing, there is something called what I can say is the table is called I forgot the name. Okay, it can be like this. One way is forming a table. Another way of representing is 000, 001, 010, 011, 100, 101, 5, then 6, then 7. This is called state diagram. That is the word I'm searching. State diagram. Initially it will be 000, 1, then 2, then 2 to go to 3, then 3 to 4, then 4 to 5, then 5 to 6, 6 to 7, back to 0. This is called state diagram. State diagram of up counter, 3-bit up counter. Okay, if it is a 4-bit up counter, it will be from 4 zeros to 4 1. 4 1 is 15. So 0 to 15 you will count. Okay, and remember that it need not to be always 0, 1, 2, 3. It can be of any sequence 0, 3, 7. Random number also you can try to get the output. Okay, so this is the first example, easiest example I am taking. So this is the question is design a 3-bit up counter using JK flip flop. For this, the state diagram is this, and this is the table I have formed. Okay, next thing here, what you know the first, you know the output. So you have to decide what should be the input. So if the present state is 000, the next state is 001. If 001 is the present state, next state is 010. If 010 is the present state, next state is 011. If 011 is the present state, next state is 100. Likewise, I can say if 111 is the present state, next state should be 000. Likewise, it will be repeating. These are called states. Totally, how many states are there? I have totally 8 different states. Okay, this 0, this is the QA bit, QB bit, QC bit. So I need 3 flip-flops. For each state, I need 3 flip-flops. Those flip-flops are JK flip-flop. The outputs are represented as QA, QB, and QC. So first step is write the state diagram. Okay, the next step, you can go for the state table. State table. Okay, in state table, what we will say is we will be comparing the present state and the next state. Present state means n. Next state means n plus 1. Okay, so what are the flip-flops I'm taking? QA, QB, QC, similarly QA, QB, QC, right? So three flip-flops output I'm taking, right? I can make it complete the table. Okay, let me fill the present state and next state. Initially, what will be the values of the first state, present state 0, 0, 0. If I give the clock pulse, what will be the next state? 1, 0, 0, 1. Then if the present state is 1, next state is 2. 2 is 0, 1, 0 is 2. If the present state is 2, 0, 1, 0, the next state is 3. If the present state is 3, next state is 1, 0, 0, 4. If the present state is 4, next state is 1, 0, 1, 5. If the present state is 5, next state is 6, 1, 1, 0. If the present state is 6, next state is 7. If the present state is 7, next state is back to 0. Okay, see this diagram only I have represented in the tabulation form. A state diagram in the tabulation form is called state table. It relates the present state and next state. Present state I am using the notation n, next state I am using the notation n plus 1. Okay, right. Now we have to decide what flip-flop we are using. As I said earlier, we are going to use only JK flip-flop. Okay, so we have three flip-flops. So first flip-flop is A flip-flop, second flip-flop is B flip-flop, third flip-flop is C flip-flop. We give the name for the first flip-flop input as JAKA. First flip-flop input. Second flip-flop input is JBKB. Third flip-flop input is JCKC. Okay, these are the inputs. Okay, fine. Now already we know the state table. Okay, you can state table. I request every one of you to write it separately. Note down this table of JK flip-flop. If you write it separately in a paper, then it will be easy for you to fill the table. Okay, has everyone written this table for JK flip-flop?
Yes, sir.
Yes, okay, then only you can follow it easily. I will take 1 minute and you can write it out. Okay, this table. Qn plus 1, you have to compare. Likewise, you have to put what is corresponding JK. Okay. Okay, hope you have written. Right. Now we come back here. See, what you have to compare is present state QA and next state QA. Present state QB and next state QB. Present state QC, next state QC. Okay, while comparing this QA and this QA, you have to fill the JA and KA. While comparing QB and the next state QB, you have to fill JB and KB. While comparing JC and QC and the next state QC, you have to fill JC and KC. Okay, right. Let me start with one example. Okay, so I'm going to compare this 0 with this 0. Okay, present state is 0, next state is 0. So what should be JA and KA?
J0, K,
Don't
anything.
Don't care.
Don't care.
Don't
Superb.
care.
Fantastic. Good. Very good. Okay. What about the next one? I need some other people to answer. If the present state is 0, again next state is 0.
JB is 0 and don't care KB.
Okay. Yes. Again, good. It is 0 and don't care. Okay. Let me go to the next one. This QC and with this QC 0, 1. I need some other answers.
1 and don't care.
1 and don't care. Fantastic. 1 and don't care. Okay. Yes. Can someone say quickly? I shall fill these things. Yes. What is this? Here. Yeah. Yeah. Please.
0 and don't care.
0 don't care. Here.
1 and don't care.
1 don't care. Okay. Yes. One girl student is yes. Let her answer. Yes.
Don't care 1.
Don't care. don't care 1, yeah. Yes, the here
0 and don't care. 0 don't
0
care.
don't care, good. Here
Don't care and 0.
Don't care 0.
0 fine. Here
1 don't care.
1 don't care, yes. Here
1 don't.
1 don't care. Okay, someone cross check. Okay, I don't have the answer also. Okay, so someone has to cross check. Okay, yes. Yes, here 1 0
Don't care and 1.
don't care and 1 1 0 don't care and 1 1 1 don't care 0, then 0 0 0 don't care, then 0 1 1 don't care, 1 1 don't care 0 0 1 1 don't care, 0 1 no 1 0 don't care 1 1 1 don't care 0 1 1 don't care 0 0 1 0 1 1 don't care, then 1 0 don't care 1, then this is don't care 1, again 1 0 don't care 1. Okay, yes. So we have filled the table. State table as done. Okay. Now the important thing is now we have to construct the K map. We have to find the expression for JA separately, KA separately, JB separately, KB separately, JC separately, KC separately using present state as inputs. Okay, this nth state as inputs. So with this as inputs, for this we have to plot the K map. So we will be getting separate expression for JA, KA, JB, KB, JC and KC. Right? So I think I can scroll it down and it will be easy for me to write the K map. Yeah, this is okay for me. First thing, I have to using present state, that is your n, within bracket I can write QA, QB and QC. Draw K map for JA separately, KA, JB, KB, JC, KC. Okay, so okay. So first thing I will draw for JA. I need 8 box K map. Since I have 3 variables QA, QB and QC, 8 box is required. Okay, here I am taking QA in the present state. This is QB, this is QC, 0 0 0 1 1 0 1 1, sorry 1 1 1 0. There should be a single bit change between the adjacent boxes. So it is 1. Have anyone tried yesterday? I gave a question to you know. By changing swapping these things 0 1 and 1 0. Have anyone tried? Yes or no? Or today you will try? Yes, anyone? Yes, anyone? Huh? Yes. Has anyone tried? Yesterday, I said that you exchange this 0 1 and 1 0. You still get the same answer. Has anyone tried yesterday? Yes or no? Or today you will try?
Sir, today we will try, sir.
Yes, that will be good. Yeah. Today I will send that PDF also. You try for that and you will say your results tomorrow to me. Okay. Yes. Okay. Now we will fill the table. If QA, QB, QC all are 0, what is JA? 0. So fill it 0 here. Then 0 0 1. 0 0 1. What is JA? Again, that is also 0. Then 0 1 0. It is 0. 0 1 0 is here. Okay, so that is also 0. 0 1 1. it is 1. Okay, then we can see 100, it is x, 101 it is x, 110 it is x, 111 it is x. So here everything is x. Here after this everything is x. Don't care. Okay, don't care is like I can say it will help us to form the group. Don't care can be 0 or 1. Okay, you cannot, there is no need to group everything. You are grouping this 4, I mean quad, I can assume this all 0. There is no need to group these 2, these 4. But while grouping this one, you can assume this x as 1. Because this can be 0 or 1, so you can easily assume this as 1, so you can group it. Okay, so I'm going to group these 2. Okay, this corresponds to JA equal to what is common? QB and QC. What is QB and QC? Here this side there is nothing common. Here it is QB and QC. So this is the expression for JA. Next is we'll try for KA. KA. For that again we are going to form an 8 box. We have to draw for present state and next state. Yes, I need your answers. We are going to draw for present state or next state. We are using these values or this value.
Present state, sir.
Present state. Remember, okay, you should not make mistake in the exam. You have to use the present state. Okay, right. Now all are 0. 0, 0, 0. It is x. Okay, so I can quickly draw. Right, I shall fill it up. Correspondingly, it is x. The entire first row is x because for these all first 4 values, this corresponding is x. Then 100 is 0, 101 is 0, 110 is 0, 111 is 1. So 111 is here, 1, 1, 1, 111 is here, corresponding is 1. Rest all 0. That means I can group these 2. Corresponds to Ka equal to the same thing, QB and QC. QB and QC. Right? Now we go for JB and KB. Okay, so again I have to refer the table here. Since I'm going for JB, I have to refer this 01XX, 01XX. Okay, so you see, if you refer this table, you can fill the refer this column. You can fill the JB K map. Here it should be 0, 1, X, X, 0, 1, X, X. Okay, right. Now the important K map part we are coming, right? Here I can group these 2. As I said earlier, we should always go for a bigger group, right? So I can group these 2 X, don't care, along with these 2 ones, I make it as a quad connection such that I can assume these 2 X as 1. Okay, there is nothing wrong in it. So I'm going to group this way. All 4 I am grouping. This corresponds to JB is equal to what is common left side? Nothing is common. This is 1 is common. The corresponding is QC. Good. QC. JB is completed. Next we will move into KC. Sorry, KB. KB. Again, 4 variable, 3 variables, so 8 boxes. You are going to take present inputs and you have to write the K map. Then you have to simplify, thereby you will find KB. Okay, now you can see this, right? You can see this column, that is your KB column. XX01, XX01. So it should be XX10 XX10. I can group it this way. This 4 I can group corresponding to KB is equal to QC. KB is equal to QC. Right. Now we'll move into JC and KC. QA, QB, QC 0 0 0 1 1 1 0 0 0 0 0 1 1 1 1 0 0 1 QA QB QC. Okay, if you observe this 1x 1x, so it should be 1x 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 1. Okay, see, I'm just for scrolling purpose I'm doing the right. You can write it separately, then you can fill it on your own. You try to fill it, right? You shouldn't have any difficulty. It should be like 1x. Okay, x1 1x x1 1x x1. Okay, say okay. Now you have to think how I'm going to group. I can group these two, or else I can group this 4, or else this first column and last column. The best thing to group is always go for bigger grouping. So as I said earlier, you can go for 1 box, 2 box, 4 box, 8 box, 16 box. Okay, so if you observe this, if I am assuming this x as 1, this 4 x as 1, then I can group this entire box together. Entire box together. If everything is grouped, the answer is simply 1. The answer is always, JC should be always 1. Okay, right. Similarly, we'll fill for KC. For KC, it is x1, 1x. Okay. X1, 1x, x1, 1x. I can group it. This all 8. Correspondingly, KC is equal to 1. Okay, now we got the expression for JA, KA, JB, KB, JC and KC. Now we are ready to form the circuit to design for counting upwards, up counter. So this is my first flip-flop. This is my second flip-flop, B flip-flop. This is my C flip-flop. JA, KA, QA, QA bar, JB, KB, QB, QB bar, JC, KC, QC, QC bar. Okay, now can I connect clock first? I will connect the clock. Since it is a synchronous counter, all are connected to the same clock pulse. All are connected to the same clock pulse, right? Next, you have to get the expression. Okay, go to the previous slide. What is JA QB into QC? What is KA QB into QC? Okay, this is my QB, this is my QC. I have to AND those two. So I'm taking QB and QC. I'm doing AND operation. I'm going to connect to JA as well as KA. So this is my QB into QC. Okay. Then what about JB and KB? JB and KB. Go to the previous circles. JB is equal to QC. KB is equal to QC. Here it is QC is there. This QC is coming here. So I can take it from here itself. I'm going to straight away connect. Okay. Then what about JC and KC? Both are 1. Both are 1 means I can connect it to. Both are connected to 1, or else if you are working in the laboratory means you have to connect plus 5 volt. You have to connect plus 5 volt at this point. Okay. Now we'll see the outputs. This is one output. Okay, this is QB, this is QC. QA, QB, QC. This is your most significant bit. This is your least significant bit. So if you give clock pulses, see, if I give clock pulse initially, all will be 0, then second clock pulse 0, 0, 1, third clock pulse 0, 1, 1, keep on counting. Last clock pulse, it will be 1, 1, 1. Then back to then give the clock pulse, everything will become 0, 0, 0. Right? Okay. Are you getting what I say? Are you able to follow?
Sir, please repeat this last one, sir.
The last one in the sense you need the design part or circuit and then this JK flip flop from there.
Yes, sir.
Yes, okay, no issues. I will explain again. See, since I'm using 3 bits, I'm getting 3 flip flops. Okay. Now each first flip flop I given the name A. Already go to the table and see. I have given this most significant bit as A, then is B, then least significant bit is C. So first flip flop is A, second flip flop is B, third flip flop is C. Right? From the table, from the K map, I got what is JA, what is KA, JB, KB, JC, and KC. JA is QB into QC, QB and with QC. Okay, JB is QC, JC is 1. Okay, so I'm taking QB, I'm taking QC, I am AND operation, I'm connecting to JA and KA. Right? Then what is JB? JB equal to QC is the same QC I'm taking here. I'm taking connection going to JB and KB. Then JC is 1, KC is also 1. If you're using in the laboratory, in the exam, you can put 1. If you're using practically means you have to connect it to 5 volt. Okay, is it okay now?
Yes, sir. Thank you, sir.
Oh, no problem. Is it okay means I'm happy for that. What about others? What about the other guys? Are you able to follow?
Yes, sir.
Okay. Thank you. Yes, man. Okay, man. Yes. Now, see, we're going for laboratory. Definitely, your IC would be having preset. Preset as well as your IC would be having clear option. Okay. So I can use some other color, maybe this black color. Okay, normal operation, what should we do? What should we do connected to preset and clear? For normal operation. This is preset. Yeah, please answer.
Sir, 1.
1, yes. Preset is disabled. That means you are connecting it to 1. Similarly, we are going to disable the clear also. So clear means connected to 1. This is your clear. This is your clear. This is your clear. If we are connecting both to 1, practically we will be connecting it to 5 volt. Laboratory means connected to 5 volt. In exam, you simply put it as 1. Enough. Okay. Here in QA, QB, QC, you have to connect an LED. Okay. It will be going on blinking in the fashion as is given in the table. Okay. 0, 0, 0 to 1, 1, 1 up to 1, 1 go. Again, repeat the cycle. This is your 3-bit synchronous up counter. 3-bit synchronous up counter. Okay, 3-bit synchronous up counter. Right? Okay. But again, quickly we'll see from the first, then we move into the down counter design. So as I said earlier, sequential circuit, it's of two types. One is synchronous, another is asynchronous. In synchronous, we have some more designs are there. First example I'm taking is 3-bit up counter using, I have specified the flip flop. If any flip flop is not given, I will be using D flip flop because that is the easiest flip flop to analyze. So these are the states in up counter. The lowest state is 0, 0, then 0, 0, 1, 2, 3, 4, 5, 6, and 7 back to 0. This sort of diagram is called state diagram. Okay, because it is specifying the states. Total number of states here is 8 states are there, 0 to 7. Next, once you know the state diagram, you can go for the state table. State table is nothing but you are going to decide, you are going to compare the present state and the next state. Okay, we know the present state, we are going to, we know the next state. From that, you we will write the present state and next state. Then, based on the present state and next state, for each of the output, we will decide what is the input, JA, KA, JB, KB, JC, KC. Now we can understand what is the advantage of D flip flop. We are using D flip flop means only one, instead of JA, KA, you can simply write DA. Instead of JB, KB, you can write DB. JC, KC, you can write DC. Just you have to compare each bit. You know the state table for JK flip flop, you fill these things. Okay. Then for each JA, KA, JB, KB, JC, KC separately, using present state as input, go for the K map. Go for the K map. Okay, from the K map, you reduce it, find out the expression for JA, KA, JB, KB, and JC and KC. Once you got this expression, you can go into the circuit. So first draw the empty flip flops. Okay, skeleton of flip flop JA, JB, I mean A flip flop, B flip flop, and C flip flop. Then give the connection as per the expression you got it in the previous slide for JA, KA, JB, KB, JC, KC. Okay, then you take the output QA, QB, QC connected to LEDs. Clear, preset are all interconnected, connected to 1 or 5 volt, and all are connected to same clock pulse, and that is why it is called 3-bit synchronous up counter. Right? Is it okay?
Yes, sir.
Okay.
Yes, sir.
Yeah, fine. Okay, I'll take a small break. You can, if any doubts, you can ask in the meantime. Next, we will design the up counter or BCD count, down counter. Take 1 minute break. Okay, I think you can proceed. Next, we will move into down counter design. Okay, I think a down counter you can try on your own. That will be good for you. Okay, I think a down counter will be good for you. I can go for some other counters. Can you try down counter on your own? Is it possible? Okay, I will guide you to some extent. Okay, yes. Second question is 3-bit synchronous down counter. Okay, synchronous down counter means it will be starting from 7, then it will go to 6, then 5, 4. Oh, no, 5 means next is 4. 4 is 100. Then 3, 011. Then 2. Then 1. Then 0. Okay. So based on this, we are going to fill the state table. We know the state diagram. We will quickly fill the state table. I think I can now use D flip-flop. Okay, you have to use D flip-flop. I will say in the question itself, using the easiest flip-flop is D flip-flop. This is the present state. Next state. Again, I give the name QA, QB, QC. Present state is N. Next state is N plus 1. QA, QB, QC. Okay. What is the first state? In up counter, we'll start from down counter, we'll start from 7. 7 down means 7, 6, 5, 4, 3, 2, 1. In that order, we'll go. In up counter, 0, 1, 2, 3, up to 7, we'll go. Then we'll go to 0 again. Okay. So 7. Next state is 6. What is 6? 1, 1, 0. The present state is 6. Next state is 5. If the present state is 5, next state is 0. If the next state is 4. The present state is 4, next state is 3. If the present state is 3, next state is 2. If the present state is 2, next state is 1. If the present state is 1, next state is 0. If the present state is 0, the present state is 0, next state is 7. Is the table okay? The table okay for you?
Yes, sir.
Okay, nice. Okay, then we'll go for the inputs. What flip-flop I recommended? The question itself, I clearly say that you have to use D flip-flop. So I have 3 inputs, QA, QB, QC. So I need 3 flip-flops, DA, DB, and DC. DA, DB, DC. Okay, why I prefer this D flip-flop? What is the advantage I get over JK flip-flop?
It has less number of inputs.
Yes, JK needs 2 inputs. You have only 1 inputs. Then any other thing?
It is easy.
Yes, it is easy to remember the state table because if you need 1, you have to give 1. If you need 1 in the next state, you have to give 1. If you need 0, you have to give 0. Okay, so next state is simply the input. If you give the input, that will be coming into the next state. That is why, what is the other name for D flip-flop? What is the other name for D flip-flop?
Delay.
Delay flip-flop. And it is also called transparent flip-flop. What is inside, that is outside. Okay. Okay. So this is 1, 1, 0, 1, 0, 1. The same. If you need this value, you have to give that as input. 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now we go for K-map. I think I can draw K-map here itself. From using the present state as input, draw K-map for DA, DB, and DC separately. So first I will draw for 8 variables, so 8 box K-map. 3 variables, sorry, 3 variables, so I'll go for 8 box K-map. They are QA, QB, QC, 0 0 0 1 1 1 1 0 0 1. You will try to fill 0 0 0. We're here. See, look at the order. 0 0 is here. Corresponding is 1. Then 0 0 1. 0 0 1 is here. Corresponding DA is 0. 0 1 0 is here. Corresponding it is 0. 0 1 1 corresponding is 0. 1 0 0 is corresponding is 0. Then rest all it is 1. Okay. Yes. Okay, now we have to go for K-map. We have to join these two. We can group these two as well as we can group these two. This we have to group it separately. Okay, for this it is QA, up in the top it is QB. For this it is QA, the top it is QC. For this it is QA bar, there it is QB bar, QC bar. Right? So DA is equal to QA bar, QB bar, QC bar, QA, QC, QA, QB. Then it is DB. For DB, 3 variables, so 8 box came up again. QA, QB, QC, 0 1 0 0 0 1 1 1 1 0. Try to fill it up. For 0 0 0 it is 1. 0 0 1 it is 0. 0 1 0 it is 0. 0 1 1 it is 1. Then 1 0 0 it is 1. 1 0 1 it is 0. 1 1 0 it is 0. 1 1 it is 1. Okay, so I had to go for grouping. So likewise I can group, likewise this is also I can group it like this. Okay, so this corresponds to DB is equal to QB, QC, QC bar, QB bar plus QC bar plus QB, QC. And see, thing about this is, it is an, what gate is this? Can anyone say? What gate is this? What gate? What gate is it? What operation?
XNOR.
Yeah, fantastic, man. Good. Your name?
Sir, Ritik Sahu, sir.
Ritik Sahu.
Yes, sir.
Ah, good, man, good.
Thank you.
Okay, yeah. Okay, it's an XNOR gate, right? So QB XNOR symbol is one dot and circle. QC. So I can write it separately. It is X. So simply E. I know not that X. I have to put X. XNOR gate. This indicates XNOR gate. Okay. Now go for DC. DC. Go here. QA, QB, QC, 0 0 0 1 1 1 1 0 0 1. Okay. You can see I can okay, try to fill it up. I have to refer the table. 0 0 0 it is 1. Help me to fill. Okay, what about 0 0 1? Please help. 0 0 1 1.
0
0. No. 0 1 0 is 1. Okay, am I right? 0 1 0 is 1. Okay, 1 0 0.
0
Oh, cool. Look at very
One,
closely.
one, one.
Yes,
One.
100 is 1. Yeah, fine. Okay, 101,
0.
0. 111. Yes, I will scroll the table. Yeah. 111,
0.
0. 110,
1.
1. Fine. Sorry. Okay. Okay. Now, see, immediately our mind would be saying that I can group it these two and these two. But I said many times, last column and first column are adjacent. So always go for bigger group. So these two and these two can be grouped like this. So correspondingly, DC is equal to, there is nothing common in the left side. Here it is common is 0, 0 is common, 0 corresponds to QC bar. So DC equal to QC bar. Okay, so we got the expression for DA, DB and DC. Now we can go for the circuit diagram. So first is develop the skeleton of this flip-flop circuit. 3 flip-flops I'm drawing. You follow what? Just you follow. It's very easy to do. DA, QA, QA bar. DB, QB, QB bar. DC, QC, QC bar. Connecting to same clock pulse. That is why they are called synchronous. Okay. Now the outputs are, these are the outputs, green line. I'm going to connect it to LED. Okay. What does DA expression? DA expression is very big. Let us see it again. DA is QA bar, QB bar, QC bar, QA, QC, QC, QA, QB. Okay, so we need one OR gate, 3 AND gates. Okay, so I will put the first OR gate. Three AND gates we need. Okay, right. So it is, see, it is common. You see, if instead of taking lines, see, I have to take a QA bar, QB bar, QC bar, and I connect it to this AND gate. Then QA and QC, QB like it connect and connect it to OR gate. That is one way. Better, I request you all to just you write the expression QA bar, QB bar, QC bar. So you can write it here simply. QA bar, QB bar, QC bar. Here it is QA, QC. Here it is QA, QB. Take these all AND gate connected to OR gate. It is the same. Instead of having so many wire connection, it may look confusing to you. Okay. So this writing this way is also okay. Right? Then what is DB? DB is QB, QC is XNOR operation. That you can do. What is XNOR gate? So this is my XNOR gate. XNOR. QB and QC, we have to XNOR. QB I am taking. QC is coming here. Okay, right. What about DC? DC equal to QC bar. QC bar is here. So I can take it. Okay, so this is your QA, QB, QC. This is your LSB. This is your MSB. MSB, right? If you wish, you can go for preset and clears. Connect out to 5 volt. So this is your 3-bit synchronous down counter. Why it is called the synchronous?
Dependent, because it is dependent on clock, sir. All the
Depend
three
on
are
clock?
dependent
No, no, no. The perfect
So
answer
all
is
three are connected to same clock.
yes, all three will be triggered by the same clock pulse, not independently. This clock pulse will trigger all the three flip-flops at the same time. That is why they are called synchronous. And note out one more thing, synchronous circuits are easy to design because it is a systematic procedure. Okay, because first what we do, we have the state diagram, then go to the state table, find the inputs, then go for the K map, find the expression, then go for the circuit. Systematic procedure. In the next class, we will see asynchronous. For asynchronous, you need intuition. There is no strict procedure. Okay, the intuition only can solve the asynchronous circuit or asynchronous circuit. Okay, right. So this is regarding your what I can say, down counter, right? 3-bit synchronous down counter. In your syllabus, there is another counter called BCD counter. Okay, can you say what is a BCD counter? What is BCD? What is BCD? No idea?
No, sir.
BCD is binary coded decimal. Just a minute. Binary coded decimal. Binary coded decimal. Okay, so we know what are the decimal numbers we know? 0 to
9.
9. 4, 5, 6, 7, 8, 9. These are the decimal numbers. Okay, if you want to code it binary wise, what is 9 actually in binary? Help me. 1001 is 9. 8 is 1000. 7 is 0111. 6 is 1100. No, sorry. 6 is 0110. 5 is 0101. 4 is 0100. 3 is 0011. 2 is 0010. 1 is 0001. 0 is all are 0. Okay, right. This is the binary coded decimal. These are the decimal numbers. These are the decimal. This is your BCD, binary coded decimal. Okay, right. Now, the difference between the binary and BCD is, suppose, if I say number 11, decimal number 11, leave it 12. 12. 12 in binary, what is 12 in binary? 8421. So 8 plus 4 plus 00. This is in binary. But the same 12 in binary coded decimal, one you should separately say 001. Two we have to separately say 0010. Can you get what I say? Can you understand the difference between up to 9? Both the binary and BCD are the same. But 10 means what we do? Binary. 10 means 0, 1, 0, 1, 0. But in BCD, 1 separately, 0 separately. The example I am given here is 12. 12 in binary is 1100. But 12 in BCD is 1 we have to separately code, 2 we have to separately code. Okay, where we are using this is if you want to drive and 7-segment display in railway station, digital clock and all, we can see 7 segments will be there. For that, the input, everything we need, the things in each digit should be coded. Okay, 12 should be coded separately, means 2 should be coded, 1 should be coded. That is BCD. Okay, are you okay with this?
Yes,
Yes.
sir.
Okay.
Yes,
right.
sir.
Can anyone help me to say a number 13? Or I can say 14. Number 14 in binary. What is 14 in binary? Help me, please.
0001.
Okay, you are saying in BCD, right? Okay, let me first write BCD. Yeah, good. What is in BCD? Yes.
0.
No. First one by one. First you say BCD or binary. You select. What you are going to say?
01.
First you are saying BCD or binary.
110.
Okay, say some girl student was answering. Let give her a chance. Okay, what is your name?
Sir,
What's your name?
1
Okay, you say for binary. Yeah, say for binary. 1 1
1
1
Triple 1 0.
0. Good. For BCD
0001
0001. For 4 it is
0 1 0 0.
01
Okay,
0
ma'am.
0.
That's it. That's it. Good. Okay. So you are very clear with the binary and BCD. Why we need BCD also? You be clear, right? And to drive a 7-segment display, we can see the digital clock. The numbers will be in 7-segment, right? So, for example, if I say the time is 9 o'clock, 10 o'clock means 10 means 1 is separate, 0 is separate. Am I right? In a clock, digital clock. Okay, smartwatch, you are seeing a number 10 is there. So 1 is separate, 0 is separate. 12 is there means 1 is separate, 12 is separate. Okay, that is why BCD. Now there is a topic in your syllabus saying that binary coded decimal. You have to count this. So what is binary coded decimal? Counter means 0, next state is 1.
1.
Next state is 2. After 2, next state is 3. After 3, it is 4. After that, it is 5. 5 after 6, then 7, 8, 9. After 9, again it's go to 0. 0. Yeah. No 10. Because 10 we don't have. 10 means separately you have to code for 1 and 0. Right? So this is the BCD counter. Okay. So definitely how many inputs, how many flip-flops you require for this? To implement this counter. How many flip-flops?
Sir, 4.
4 flip-flops. Yes, you need 4 flip-flops. For each bit, you need 1 flip-flop. Okay, right. Then what is other difficulty? How many unused states are there? Your 9 is there, 10 is not there. Am I right? 10 is not there, 11 is not there, 12, 13, 14, 15 is not there. Okay. States like, I can write it separately. 10, 1, 0, 1, 0 is not there. 11 is not there. 12 is not there. 13 is not there, 14 is not there, 15 is not there. These are unused states. Unused states. For unused states, you can use don't care condition. You have to use don't care X condition, don't care condition. Okay, I give it as an work to you. You try to write the present state, next state table, right? Then present state, next state table is simple for you. Okay, if you know this diagram, from this diagram you can write the present state and next state table. You use D flip-flop, fill it. While going for K map, definitely you are in a position to fill these values. These unused states will be there. Okay, what will be the K map? Now K map for 4 variable, how many boxes required? For a 4
16.
16 boxes. But we
16.
have
16,
only
sir.
10. Yeah, in our table we have only 10. Okay, 0 to 9 only we have. Remaining 6 is what? Unused state, these things. For these things, you just mark X, unused X, or is don't care condition, then go for K-map simplification, K-map simplification. Okay, find out the expression for DA, DB, DC, and DD. Okay, then you can submit in the next class. Can you do it?
Yes, sir.
This is the yes sound we have. Can you bit stronger? Yes or no?
yes, sir.
Yes.
Yes.
Good.
Yes,
Good.
sir.
Okay,
Yes,
give a honest
sir.
try. Give a honest try tomorrow. Okay. I think I can stop here. Right? Any doubts you have? I will see. If you have completed the solution, just WhatsApp me. I will correct you. Whether it's correct or not, I will check it for you. Okay. And I will share these slides to you also. Any doubts do you have? Any doubts or clarification? Okay. If you don't have any doubts, give some time. Any doubts? No means no, yes means yes. You say something. Yeah.
No, sir.